Physics for everyone welcomes you. Today topic Thomson experiment determination of specific charge E by m of an electron. Here we learn the principle of this experiment, arrangement of experimental setup, determination of velocity of cathode ray, then determination of specific charge without the application of electric and magnetic field. Next, we will be determining the same specific charge only by applying uniform electric field. And then last, determination of specific charge by applying only uniform magnetic field. This last topic we don't learn. We will be understanding it with the help of determination of specific charge only due to uniform electric field. Thomson experiment is considered as one among the landmark experiment for the birth of modern physics. This is the diagrammatic representation of Thomson experiment. Look at carefully. The principle. In the presence of electric and magnetic fields, the cathode rays are deflected. By the variation of electric and magnetic fields, the specific charge, the charge per unit mass of the cathode rays is measured. The cathode rays is electron beam. Arrangement. A filament connected to a battery, and an anode and a cathode connected to a high voltage battery, and the screen. A highly evacuated discharge tube is used, and cathode rays produced at the cathode are attracted towards the anode disk A. Anode disk is provided with pinhole in order to allow only a narrow beam of cathode rays. Check out, the beam goes through the pinhole and hits the screen. Other rays are deflected away from the anode. Here you have a deflecting plate given to a high voltage. The positive plate is on the top and the negative plate is at the bottom. Because of this electric field, right, the electron are attracted towards the positive plate and it hits the screen at P. These cathode rays are now allowed to pass through the parallel plates which are maintained at high voltage. Here you have a north pole and a south pole. The north pole is on the top of the screen, the south pole is at the bottom of the screen. These are all the poles of the same electromagnet or a horseshoe. Better, it is an electromagnet. Good? Okay. Now these electron beam are vertically deflected downwards and hits the screen at P prime. Now we apply both electric and magnetic field. What would happen? These electron beam neither go vertically up nor vertically down. It will go straight and hits the screen once again at the original place O. Further, the gas discharge tube is kept in between the poles of the magnet such that both electric and magnetic fields are acting perpendicular to each other and perpendicular to the direction of flow of cathode ray. No upward deflection, no downward deflection, only straight line path of cathode ray hits O. When the cathode ray strikes the screen, they produce a scintillation and a hence bright spot is observed. This is achieved by the screen is coated with zinc sulfide. Look at that screen. The zinc sulfide screen is coated to get the scintillation, fluorescent screen. Determination of velocity of cathode ray. Here you have the deflector plate. The electric field is from positive plate to negative plate. The electron now goes into the electric field, get deflected upward. The electric force is in the upward direction. Remember, this is electron which is negatively charged. It is attracted towards the positive plate. Now, this is the magnet. The magnetic field is from north pole to south pole. And this electron, when it get into the magnetic field, it is vertically deflected downward. The magnetic field is in the vertically downward direction. We call it as FB vector. Let us have now both the fields. What would happen? This electron experience both the downward force as well as the upward force. The downward force is FB vector, the upward force is FE vector. So the electron beam goes in straight line. For a fixed electric field between the plates of the magnetic field is adjusted. How you adjust the magnetic field? By adjusting the current in the electromagnet. If you change the direction of the current, the poles of the magnet will be changed. Then what would happen? The deflection never brought to zero. Once again, it will increase because the electric field and magnetic field will be in the same direction. Right? You cannot bring back the electron beam to the original spot. That's not possible. So we have to have the electric and magnetic field in such a way that they act vertically upward and vertically downward. The forces must be up and down. This means that the magnitude of the electric force is balanced by the magnitude of the magnetic force. So let E be the charge and V be the velocity of the cathode rays, then the electric force is equal to the magnitude of electric force is equal to the magnitude of the magnetic force. So EE equals EBV. We find the velocity equals E by B. Let us write this. This is a very important relation we will be using in our further derivation. Determination of specific charge. Here you have the accelerating cathode and anode system. The electron is accelerated through the pinhole. The energy to the electron is given by the battery. The electrical energy of the battery is EV. This is given to the electron. The electron takes this energy and it goes with the high velocity with the kinetic energy half mv square. Right? So the battery energy is converted into kinetic energy of the electron. Since the cathode rays are accelerated from the cathode to anode, the potential energy of the electron beam at the cathode is converted into kinetic energy of the electron beam at the anode. Let V be the potential difference between the anode and cathode, then the potential energy is given by EV. Then from the law of conservation of energy, EV equals half mv square. E by m equals v square by 2v. So we can substitute the value of velocity here as E by B. We get E by m equals 1 by 2v E square by B square. Let us substitute the value of E, B and capital V. We get the value of E by m as 1.7 into 10 power 11 coulomb per kg. Determination of charge. Deflection of charge only due to uniform electric field. Here you have the deflector plate. The length of the plate is L equals Vt. What is V? It is the velocity of the cathode ray. What is T? T is the time taken to travel this deflector plate through a length L. Right? So L equals Vt. Now this electron beam, this is the zinc sulfate fluorescent screen, and this electron would travel in the straight line path, but that's not possible because of this electric field. It will be deflected upward because it is negative charge, and it is deflected towards the positive plate and hits the screen. Right. The electric force is Fe in the upward direction. Now at the end of the plate, the upward displacement is y prime, and on the screen the upward displacement is y. The initial upward velocity is 0. This information we will be using in our derivation. When the magnetic field is turned off, the deflection is only due to the electric field. The deflection in the vertical direction is due to the electric force. The deviation of the cathode rays from the original position on the screen is given by y equals c time y prime. Y prime. The c is the constant, proportionality constant that can be given by the manufacturer of the cathode ray tube, right? It depends upon the geometry of the cathode ray tube. Y prime is the deviation of the cathode ray at the end of the deflector plate. We are going to use the formula, equation of accelerated motion formula. S is equal to ut plus half at square. In this, the S is given by y prime, u is given by 0, a is given by ae, acceleration due to electric field. Let us have a simple replacement. Y prime equal to initial upward velocity is 0 into t plus half time acceleration due to electric field into the time will be length by velocity. The time taken by the cathode ray to travel the length L will be given by L by V, right? So Y equals C times ut plus half AET square. Let us substitute. Initial upward velocity is 0. Then we substitute acceleration. AE equals the electric force by mass. Then we substitute time travel by the cathode ray through a length L. T equals L by V. The time taken by the cathode rays to travel a length of the plate L with the velocity V. T equals L by V. So Y equals C time half Fe by M multiplies L by V the whole square. Substituting the electrical force equals E times capital E is the charge of the electron, capital E is the electric field intensity. So Y equals C time 1 by 2 E by M multiplies L square by V square. Now you remember that the velocity V is replaced by E by B. So I get y equals c times 1 by 2 times E by M multiplies L square by E square multiply B square. Here one E is getting cancelled from the numerator and in the denominator E square. So we get y equals c times 1 by 2 E by M multiplies L square B square by E. So E by M equals 2 EY by CL square B square. I keep E by M on the right hand side, taking the remaining term to the left hand side and changing the sides. So E by M equals 2 EY by CL square B square. E by M equals 2YE divided by CL square B square. Substituting the values on the right hand side, the value of specific charge is calculated. So E divided by M equals 1.7 into 10 power 11 coulomb per kg. Note, the specific charge is independent of the gas used in the discharge tube. Second, the nature of the electrodes. Right. Here, when you use only magnetic field, the force Fe equals Ee is replaced by the magnetic force Fb. Fb equals Bev. Then we have to continue to get an expression for specific charge by using only magnetic field.